we finished with the discussion of the geometry of the crossing equation, and we had some figures corresponding to truncations in when you take the difference of the blocks to be just three-dimensional vectors. So now I want to do things a bit more formally and more generic, and also show you how these functionals that we spoke about last time can actually be computed numerically in practice. But okay, so the first thing that we're going to do is write down what the generic crossing equation looks like in a CFT. Okay, so maybe I should put some little bars here. So this is the most general crossing equation. So what's this? Here, generically, we are looking at an ensemble of 4-point functions of various operators. So we're not focusing on a single correlator now. We can consider several ones. The operators, they could have all kinds of quantum numbers that you want. They don't have to be scalars. They don't have to have the same conformal dimension. So any local operators in the CFT. So the crossing equation for this ensemble of correlators always looks something like this. So again, we are looking at a crossing equation that perhaps looks like this, again, schematically. So we are exchanging operators O in the intermediate channel. These operators O can have various kinds of quantum numbers. And to each such operator will correspond a vector of OP coefficients. Okay? You get a vector because generically when you take two operators and you fuse them to give a third one, there could be many discrete ways in which you can do this. So there will be multiple OP coefficients. And also, we are looking at several correlation functions at the same time, so you need to tell me how that operator couples to the external operators appearing in these correlators. Okay, so there are many OP coefficients that appear here. Then this G, in general, it's a vector of matrices. So the matrices arise because now the OP coefficients are vectors, right? So it's an ensemble of matrices, and it's also a vector because there are several crossing equations. So this is the most general thing, and so before, in the simple scalar case, we had sum of lambda squared delta L times some f functions, right? This f function depended on the quantum numbers of the external operators. So now that appears here. These psi a's are the set of external operators that you chose, whose correlators you are examining. So these objects, they will depend on the quantum numbers of those operators, and they will depend on the quantum numbers of the exchanged operators. And they will also depend on which channel you are exchanging the operator and so on. But so this is the generalization of this. So this lambda gets moved here, and then the equation looks like this. So what we know is that in these quantum numbers, there's always at least one continuous label, which is the label corresponding to the conformal dimension. Generically, the other quantum numbers are discrete. So as an example, since this is a bit too formal, let's consider the case where you would bootstrap 3 correlators of operators which I'll call sigma, then an operator which I'll call epsilon. And we consider these 3 correlators and see what the crossing equations look like. So in this case, it's actually quite simple. So let me call this 1, 2, 3. So let me look at a particular set of crossing relations. Well, for one, we already know what it is, right? I showed you in the last class. So the equation just looks like sum of some OP coefficient square corresponding, so sigma, sigma with operator O, times that f function, which depends on O. So I'm going to omit the label. Well, okay, let me put O. And it depends on the, well, here, this is it. It only depends on the dimensions of O. So I'm going to be a bit schematic here. But this is the equation that I wrote down last time. And last time I put the identity on the right-hand side, but now I just keep it on the left for simplicity. Okay, it corresponds to when O is the identity operator, these coefficients are 1. Anyway, you can just put it on the left-hand side. And so you have this sum over operators. Then equation 2, it's similar. So I get, again, I have some sum over operators. But now, if you do the OP, for instance, in this channel, sigma epsilon, sigma sigma, then you see that the OP coefficients will not appear squared because you'll get sigma sigma O and sigma epsilon O. And now there will be a different f that appears here. Because recall that the f's, they are simply the difference between the conformal block and the cross-channel block. And the blocks, they know about the external operator dimensions. Okay? So this prime just means that this guy knows about the fact that delta sigma is not the same as delta epsilon. Okay? So I'm just putting a prime. Then equation 3. So here's something new happens, is that you could consider a channel where you would see the OP coefficient epsilon, epsilon O. I will not consider that channel. I will consider the channels only when you fuse operator sigma epsilon. Okay, so sigma epsilon or sigma epsilon. Okay, 1, 3, and 1, 4. And so now you get a sum where, again, you see coefficients squared. Sigma epsilon O appears twice, so it's squared. And again, there's some other f's. Okay, I mean, they're simple. It's just block minus cross block, but the conformal blocks, they include the fact that you have, that the dimensions of the operators are like this. Okay?
Why do you consider just this type of
Why can I?
consider just sigma epsilon?
No, you can add more. You can add more, yes. This is not, I'm not saying that this is the full set of constraints that arise from these correlators. But you see, if you do the OP in the other channel, you'll see a new class of OP coefficients appearing, which is epsilon, epsilon with O. And so then it would be better to also include more correlators, which will involve that OP coefficient, such as epsilon, 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 epsilon. They will know about these coefficients as well. Whereas here I have a closed subsector where there are only 2 types of OP coefficients that appear. Sigma, sigma O, and sigma epsilon O.
Shouldn't be in the same sum. Why should be in the same sum of the
Sorry?
So you have a sum, right?
Yes. Over O's.
See that it should be, I need to know how can you separate this sum in 2 parts. And one part is just these coefficients, and the other part is coefficients sigma, sigma.
No, I'm not doing, I'm doing this with this,
Right.
and then this with this. So it's always it's the same thing in the direct and the cross channel, right? It's always sigma epsilon, sigma epsilon.
Yes. But
These are 3 equations. These are 3 equations which have to hold, right? Okay?
You have ST and U channels, and you can equate ST, SU, and T.
I'm not saying that I've used all the channels. This is what I just said. I'm not using all the channels, because then you would want to include more correlators. Okay? Anyway, you see that something new happens here, is that this is positive, those are positive, this is not positive. Not necessarily. Okay? So let me write this. How would I write this in this fancy way? Well, I would write lambda O is lambda sigma sigma O, lambda sigma epsilon O. and then this G is just going to be a vector of matrices F0, 0, 0, 1 half F prime, and whatever, 0, 0, 0, F prime prime. Okay? So there's a vector of matrices, and if you dot these matrices with these vectors on left and right, you reproduce the three equations, right? Okay? So now there are two ways to proceed. Let me start with the first one. So this looks very different from what I told you about last time, which is kind of annoying because this is the most generic case. Right? This is the most general form of the crossing sum rule. But there's a simple trick that brings it back to what we had already done. So let's say that lambda O, which is a vector, we write it as its norm times the direction. So maybe I can put some vectors here. Okay? Okay? If I do this, then the equations I get now look like lambda squared O, where this is a number, right? And then I get some F's, which depend on O, psi A, and they depend on a new set of quantum numbers, if you want, which is this NO. Okay? Where this, by definition, is simply the G matrix contracted with N on both sides. Okay? So each such matrix, you contract with one of those little vectors N. Okay? And now the equation looks exactly the same as before. So this is not a matrix now. It's a vector. It's a vector of functions. But vectors, it's fine, because we're going to do Taylor expansion on the functions anyway and turn them into vectors. So this is just one big vector, right? A vector with little vectors inside. But of course, so what's the price that we've paid for doing that? Is that we've introduced a new quantum number. So now the operators, they have not only the usual quantum numbers, but they have a continuous quantum number, which is this n, which gives the orientation of the operator in the space of OPE coefficients. Okay? So now you have not only the conformal dimension, you have a new continuous parameter. Okay? But so the general logic of what I told you in last lecture still holds, except that before I was drawing lines and looking at the convex hull of lines, and now you have to draw surfaces and look at the convex hull of surfaces. But the logic is exactly the same. So you still want to compute functionals, which will, when acting on these Fs, they will be positive and which will be negative on the identity. Okay, so everything that I said before still holds for the most generic case. Okay, now this is not the usual way to proceed. It is useful for checking certain things, like determining the spectrum of these solutions to crossing. But what's usually done in practice is a different approach, which I won't go into detail, but I'll just explain what it is because it's how things are usually done in practice. So the idea before is that we wanted to rule out such equations. So how did we proceed last time? We made assumptions on the set of operators that can appear in the sum. Right? We said, well, now I only allow operators appearing in some set S, which I choose. And I try to construct a functional lambda that when acting on these Fs of O, it's going to be positive for all O in some set. Okay? So if you could find this, then you would get a contradiction with this sum rule because these coefficients are positive. Okay? Now we cannot do this, right? Because we don't have positivity. There are these cross terms here. However, we have these matrices. So these matrices will be dotted into these vectors of OPE coefficients. So there is one way in which this can work. If we can find a functional, so which will do the following. So it's a linear combination of this matrix plus this matrix plus this matrix with some derivatives on the f's. So this will be just one matrix. If we can choose a functional such that that matrix is positive definite, then no matter which choices you make for the OPE coefficients, the result will be positive, and so the contradiction will still arise. So what I mean, so again, what you have to do is that you need to construct functionals such that when they act on this G for all O in some set S, so this is a matrix, so lambda has vector indices, okay? So it's gonna dot into these vector indices and leave a matrix. So this matrix should be positive semi-definite. Okay? And then the same contradiction will arise because no matter which OPE coefficient you pick, you get a positive result. Okay? So in our example, this would look something like this. You'd need a functional which would do this. Lambda 3 f prime prime. So our functional is a vector. It has three components, lambda 1, lambda 2, lambda 3, because there were three equations. And when you dot it into that, you get this matrix, this 2 by 2 matrix, and you want to make this matrix positive semi-definite for all operators in some set. Okay? So, no, that's too strong. That's too strong.
Can you repeat the question?
Sorry. So the question is, why did I put them together? The point is that I can always choose to switch off some of those lambdas, right? So I could just set lambda 2 and lambda 3 to 0, and I would recover the bounds, the things that I had already. But now I could switch on additional degrees of freedom to find functionals that I could not find before, right? So the bounds will only increase by doing this. So this is less restrictive. I have more degrees of freedom than what I had before. Okay, does that make sense? Yes?
I guess a comment is that f written is really a tensor product of f that's 0 then 0, and the f prime is 0 then f prime then 0.
0 then f prime then 0. Sorry, I don't know. Yes?
Like it's a vector of matrices.
Yeah, this is a vector of matrix. Yeah.
Yeah, and it has 3 parts.
Yes. Yeah. 1, 2, 3. Yes. So the functional acts on the three equations at the same time. Does that clear?
The first entry will be f00, the second entry will be 0, 1 after prime, 0.
Yes. Yes. This is a vector of matrices, and lambda is a vector acting on this vector, so it will give you a matrix. Okay. So you have less conditions on the functional now. You have more degrees of freedom. This is why the bounds can become stronger.
It also says that the lambda needs to give negative on some like identity.
Yes, yes. So at least one of these constraints should be strengthened to strict inequality. Otherwise, lambda equals 0 would be a solution. Yeah. So like on the identity, you can ask it to be equal to 1 or bigger than 1 or something.
So one good thing about these n vectors that you said, usually you say that's not the way you do it. Can the n be anything since you had at least part of your coefficients always positive? Does that say n?
So in this example, it's just a unit vector, a unit two-dimensional vector, right?
Even though
There were two coefficients, right? So I'm just parameterizing this vector using an angular variable. So this is just the norm of this, and then there's an angle. So generically, you have many new continuous variables. So it gets very complicated. So this is why this is a better approach. Okay? So the price you pay here is that. Whereas before, the constraints on the functional, they were linear. It was just functional acting on something is positive. Now it's that when you act on the functional, you get a positive definite matrix. So in this case, the constraints will be quadratic, right? Nevertheless, there are efficient algorithms for constructing functionals subject to these constraints. Okay? So I will not discuss those algorithms. They are interior point methods. I will not discuss them. What I'll do is just use the fact that I can always think in terms of these linear constraints, discuss everything here, and the functionals that I can construct that way, it will be the same ones that satisfy this. Okay? So more questions? Okay, good. Okay, so now we're just going to repeat the logic. So you no longer have to think about any of this multiple correlator, or I mean, this very complicated case. It's irrelevant. So just have in mind what we discussed last time. Okay, correlator of identical operators. So last time we were discussing what I call the feasibility problem, which is you select a set of quantum numbers for which operators are allowed in the OPE, and you check, does the crossing equation have solutions? Or can it not have solutions? Well, now I'm going to do something a bit different. But as you'll see in the end, it's related to that initial problem. So suppose that you choose a set S where you know for sure that solutions to crossing exist. Like, for instance, you could take S is equal to U, so quantum numbers consistent with unitarity. For instance, I mean, it doesn't have to be this, but you should choose a set where you know that solutions exist. Okay, we know that CFTs exist, so certainly this is a good choice. So there are many, many solutions to crossing. And we want to single out a particular one. And we'll do this. So one thing that you can do is called OPE maximization. So I'm going to give two pictures of the same problem called the primal and the dual. The primal, so it's as the name says, I want to maximize for all lambda squares Okay. So this is the question I want to answer. Assuming that crossing holds, so subject to these constraints, that you have a solution to crossing, the sum over O in this set is equal to the identity. Recall, I call this the target. So this is the identity. Subject to these constraints, I ask, how can I maximize this following quantity? So it's a sum of OP coefficients times some cost. This is called the cost associated with that OP coefficient. So typically, you choose all COs to be 0 except 1. Okay? So you want to find a solution to crossing for which one of these OP coefficients is as large as possible. Okay? This will select out a unique solution in the space of solutions to crossing. So this is the primal formulation. But if you want to understand it in terms of the functionals that I was talking about, then it turns out that this problem is completely equivalent to this. So minimize lambda dot t such that for all operators in S, lambda dot f is positive. Okay? And the minimum value of this corresponds to the maximum value of, sorry, this is not 0. costs, obviously. So it turns out that the minimum of this problem is the same as the maximum of this problem. Okay? Certainly, the minimum of this provides an upper bound on this maximum. It's easy to check, right? So you start off with this, apply lambda t here, right? Then, so maybe I should do it. So suppose that you've solved both problems. Then you dot lambda with t to find out what the minimum. You already know what this minimum is. But you also know that this is the same if you've solved the other problem as the sum of operators in S for some choice of OP coefficients, lambda dot f. Right? But by construction, this is larger than the cost. So this is larger than the sum of lambda square O CO. But this was that maximum, so let me call this the cost function C. Okay? So the maximum value, sorry, the minimum value of this problem sets an upper bound on the maximum of the other. And there's a theorem that tells you that actually they match. Okay? There's no gap. The minimum of one is the maximum of the other. So if you solve one problem, you get the other one. Okay? Yes?
Aren't you normalizing lambda, like when you X on the identity?
That's here.
Yeah, so isn't lambda times d something that you normally normalize to some value?
No, not necessarily. No, here you don't need this.
Okay, so how
Because there's a cost. So these numbers, they set the scale for the functional, right? When these costs are all zero, then you need to worry about this. Here it's not. Okay? So obviously this is useful because when you solve this problem, you get an upper bound on the value of that OP coefficient, which is true for any CFT. So this is obviously an interesting question to set. Before we were talking about bounds on operator dimensions. This is a bound on the OP coefficients. Okay? But the two problems are related. So now let me tell you about the feasibility problem. So now you don't know if a solution to crossing exists. Okay? So what we're going to do is that we're going, in fact, I probably should have said it. Here I'm assuming already that we've Taylor expanded the f's. So these are just vectors. Okay? These are not functions anymore. They're just vectors. Okay? Since these are vectors with n components, okay, then let me introduce vectors wi, okay, such that the ith vector, its jth component, is delta ij times the ith component of the target. Okay? Then, and now we write the sum rule as the sum I goes from 1 to n, mu I wi, plus the sum of the operators in some set, lambda squared O, FO, and this must be equal to the target. Okay? These are positive coefficients. So I've excluded all operators outside some set S. I want to check if solutions to crossing exist using only those vectors. Okay? But as a first step, what I do is that I add some fake vectors, some auxiliary vectors, such that this equation has a solution for sure. Look, by construction, since these w's are equal to this, then a solution to these constraints is where you set the lambdas all to 0 and the mu's to 1, right, by construction. So this has a solution. And now what we want to do? We want to do an OP maximization problem where we want to minimize these coefficients. We want to send these mu's to 0. And if the minimum is when these mu's are all 0, then you found the solution to crossing. You see? So So the two problems are actually related. So the feasibility problem now is, well, you're maximize, let me write it down. So maximize the cost, which is minus sum of the mu i's. So the costs of these guys are 0 and the costs of these guys are negative, subject to this equation. Okay? So our feasibility problem is the same as an OP maximization problem. So you only need to deal with the other one. Okay? One annoying thing is that when you do OP maximization, when the algorithm finishes, you're done. Whereas in this case, you're just checking if a region is feasible, but that might not be the optimal region, right? So when I was telling you about bounds on operator dimensions, you needed to check, well, if I put a gap up to this value, is there a solution or not? And you need to solve an OP maximization problem. And you say, oh, there's no solution here. Good. But is this the optimal gap? Well, let me lower it. You lower it, you get a new set S, and now you have to do this again. So it's a lot harder. It takes a lot more time. Whereas OP maximization, you do it once and you're done. Okay, so there's a difference between the two problems. Okay? Good. So now I'd like to tell you something which is a generalization of what I told you last time, which is what happens when the minimum is achieved. So lots of nice things happened when externality was reached, right? So the functional was hugging the convex hull of the vectors. The functional had zeros. The zeros were precisely the vectors that you needed to use in the solution, and so on. So this generalizes. It turns out that there is this theorem that tells you that when the minimum of this problem is achieved, this problem, then lambda has to satisfy certain properties. So let me call them the externality conditions or optimality conditions. So these are necessary conditions for the minimum to have been achieved. So there are three. One of them is crossing. Okay. Okay, let me do it like this. Lambda square Oj f Oj is equal to t. Next condition, saturation. The functional dotted into these guys is equal to the respective costs. And the final condition, it's tangency. Lambda dotted with the gradients of these guys is equal to either 0 or positive if O, sorry, this is 0. If Oj is not in the boundary of S, and if Oj is on the boundary of S. Okay, so these are the three necessary conditions. So we were solving this problem, huh? This problem. We know that it should be related to this one, but so we're just solving this problem. And then this theorem tells you that after you've solved the problem, several things happen. A solution to crossing automatically appears, involving k vectors, and k is smaller or equal than n. What are these vectors? These vectors are the ones for which the inequalities on the functional are saturated. Okay? So we had inequalities here. This tells you that the vectors which appear in the solution are the ones which saturate these inequalities. Okay? This characterizes which operators appear here. And finally, there are these tangency conditions. So these f's, they have a continuous quantum number, right? The conformal dimension. So this tells you that the function has to be tangent. So here I said nabla A because in principle there could be many continuous quantum numbers if you have these angular variables. But in the example that I told you yesterday, there's just a derivative with respect to delta, the conformal dimension. Okay, but A labels those quantum numbers. So there are two possibilities. When you hit it against the gradients, well, if the operator is inside the allowed region, then the function has to be tangent to it. Okay, because if it was not tangent, then it would have a 0. Well, here it's not 0, it's C, whatever. But then it would keep going inside, and it would go below C. So let's set C equals 0 so that we have in mind yesterday's example. The function was tangent, because if it was not tangent, it has to have a 0. So if it's not tangent, it's not a double 0. It just goes straight through the surface, and it would become negative on some other vector. Right? So function has to have a 0 at this point. The only possibility is that it's a double 0. Otherwise, it would do this. And so here, the vectors inside this region, they would be negative. Okay? Oh, sorry, the vectors on this side. Is that clear? I see maybe some confused faces. So you recall, you have the functional splits the space into 2 bits, the target on one side and the other vectors on the other. And at externality, the functional starts getting pushed towards the vectors until it just hugs them. Okay? So this is this tangency condition. Okay? It has to be tangent. Except, obviously, if these vectors are on the boundary of the set. On the boundary of the set, it's fine. So if the set is here, then the function at this point, it doesn't have to be tangent, right? It could be doing this. This would still put all these vectors on one side. Okay? There's nothing wrong. But if there were vectors here, these vectors, they would be negative. Okay? So this is just a formalization of the things that I said yesterday, which were true for n equals 3. This just tells you that it's true in general, and it's true if you consider this multiple correlator system, blah, blah, blah. So the logic is the following. Whenever you find one of these functionals, you plot them, you plot this quantity, and you see when the inequalities are saturated, and those are the vectors which have to appear in the solution to crossing. And the solution is unique. Okay?
This nj thing is some vector.
Sorry? This nj?
Is in the boundary of S. We have this in nj.
Yeah, so you picked some set of quantum numbers.
Yeah.
This set, in the space of quantum numbers, if the operator lies on the boundary of that set, then when the functional acts on this gradient, it has to be, so I didn't explain what this is.
Yeah.
So it means it has to be inward pointing. So the function has to be growing towards the insides of the set, right? It has to be positive there. So in the case of the line, this means that if you plot lambda.f as a function of delta, it has to be this. The functional has to look like this, where this is your gap, right? So my set S begins here. So the functional here is not tangent, right? So it has a single 0, a first order 0. But then on all the other zeros, it has to be a double 0. Because if it wasn't, it would dip below the real axis. It would become negative. This is what these conditions mean. Okay? Okay. I have to speed it up a bit. So now I want to give you a method which constructs these functionals algorithmically. Okay? It's called the Simplex method by Danzig. Okay? So I'm going to simplify notation a bit. And I'm going to flip some signs. Okay, so let's consider the primal version of the problem. So we want to solve the following problem. Minimize the cost, which by definition is some sum of some C alpha A alpha, alpha in S, such that the sum of A alpha V alpha is equal to T for alpha in S. Okay, with A alpha greater or equal to 0 and V alpha T in Rn. Okay, so I simplified notation a bit. So the OP coefficients of operator O is now A alpha, where alpha labels the operator, okay, the quantum numbers. These are the costs as before. I flipped the sign, so now I'm minimizing instead of maximizing. It's not a big deal, just my notes were written this way. You can just flip the sign if you want. And these are all vectors in Rn. Instead of calling it f of O, blah, 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 I just call it V, because this is literally a vector, okay? Just a column of numbers. Okay, so how does the algorithm work? We want to find an algorithm which systematically lowers the cost. Okay? So the starting point is a feasible solution. So you have these constraints. So you need to start with some solution of these constraints. There's always a trivial way to do it, which is to introduce those auxiliary vectors, like I did. Okay? So let's just assume that you found some feasible solution. So then the vectors are split into two sets, basic and non-basic. So basic means that the OP is larger than 0, and there are n of them. Because we are in Rn, so we only need n vectors at most to solve these constraints. Okay? And the non-basic, they have OP equals 0. Okay, this is fancy terminology, but look, you just need to pick n vectors which satisfy these constraints. These are called basic vectors at that step. Everyone else, it's switched off. It doesn't appear in the solution, so they are called non-basic. Okay? So we have some sum for the quantum numbers in this basic set, A alpha k times Vk, V alpha k. This is equal to T. Okay, so we start with this. For n quantum numbers labeled alpha k inside the set B. Okay? Now, the coefficients, I can determine them explicitly. A alpha k is simply the inverse matrix dotted with T, component k, where A is V alpha 1, V alpha n. Okay? So you take your n vectors, put them in a matrix, you invert the matrix, and you find the coefficients. Right? Just linear algebra. So you have these OP coefficients, and the point is that you need to know them to determine the cost. That's the cost. So at a given step in the algorithm, you have a solution, you have these OP coefficients, and the cost is the sum when k goes from 1 to n of C alpha k times A alpha k. Okay? This is my current cost at this point. I have a solution which has this cost. Now, we want to keep going until the cost is reduced. So what's the idea? We have n vectors. How do we know if this is the optimal solution? Well, let's try to find some vector in the space S, such that when I bring it in, when I switch it on, the cost will reduce. Okay? So when I do that, what happens? So the cost will become A gamma C gamma plus the sum alpha k in B A prime alpha k ck. So I switched on a coefficient, so the cost changes. And these coefficients, the previous OP coefficients, they will change because I'm switching this on, and I have to keep the constraints true, right? So what are these guys? Well, they are equal to j equals 1 to n of the inverse matrix kj t minus A gamma V gamma j. Okay? So before I had this, and now I'm switching on a vector. So I just put that vector on the right-hand side, and so the OP coefficients will change in this way. Okay, I switch on this vector, I put it on the right-hand side. These are the new OP coefficients of the basic vectors. Okay, is this clear? Don't hesitate to stop me. Okay, so let's plug this into the cost. So the cost is now, yes?
So, is there a way to choose A gamma or I just do gamma?
You have to search. I'll tell you the conditions on gamma now. So the cost now will become what? C alpha k, A minus 1 kj tj, plus C gamma minus C alpha k, A minus 1 kj V gamma j times A gamma. Okay? So I just replaced that expression into the previous one for the cost. So when you switch on a new vector, the vector gamma, the cost now behaves in this way. Okay? So the dependence on the new OP coefficient is here. So this constant piece, we don't care. Okay? It was already there. Another question is, we introduce a new vector, but we need to introduce it with a positive coefficient, right? These A coefficients are always positive. So the question, if this quantity is negative, then the cost will decrease as you switch on this coefficient, right? So the constraint is lambda dot V gamma should be smaller than minus C gamma, where lambda by definition is minus C alpha k minus sum k 1 over n C alpha k A minus 1 kj. I called it lambda because this is the functional. This is the functional in the other picture. Okay? So you construct this quantity. These are the costs of the basic vectors. This is the inverse matrix that I showed you before. And now you need to scan over all vectors in S until you find one for which this is true. One will do. But obviously, you want to choose one such that the cost will decrease as fast as possible. Okay? There are several criteria. So you could just choose the one for which this difference is as large as possible. That's one choice, for instance. But it doesn't matter at the end of the day. The number of iterations in the algorithm will increase. So in terms of numerical efficiency, there are better choices than others. But for the purposes of what I'm saying, you just need to find one. If you cannot find one, then you're done. You've minimized the cost. Right? There's no vector that you can find to lower it, then you're done, you finished. That particular solution with those basic vectors is the crossing solution that minimizes the cost. And the functional at that point is this guy. Okay?
So is this algorithm able to find global minima or you can only find local minima?
So in general, yes, right. So you have to scan over this gamma, which is a continuous set. You need to find at least one vector which is negative, but then you have to ask the question, yes, there will be local minima, there will be global minima. Which one should you choose? So there are two choices which I'm aware of, which are good. The one is the global minimum. Okay? This is what I just described. You want this difference to be as large as possible. Okay? So that's like the slope. As you turn on this new coefficient, you want the variation of the cost with that coefficient to be as large as possible. But notice that you turn it on, but you don't know how much you will be able to turn it on. So you could have a very large derivative, but then you can only switch it on a little bit. So that's not good. Which brings me to the next step. So how do you decide how to set this new coefficient? It's easy. You start turning it on. And as you do that, these other coefficients, they will change. Some of them will increase, but some of them will decrease. And when they start decreasing, eventually one of them will hit 0. Once it hits 0, you have to stop, because otherwise the coefficient will become negative, and that's not allowed. So what you've done is you switched on one vector, and you switched off another, so you can swap them. and you have a new set of basic vectors. The cost has been lowered, you have a new set of basic vectors, and the algorithm proceeds. So let me just formalize it a little bit, but that's the idea. So, as you dial up this A gamma, the other coefficients, they are given by this, A minus 1 kj tj minus A gamma, A minus 1 kj v gamma j. Okay, I think maybe I was putting a prime. So now you dial up this coefficient, and eventually one of these guys will be 0. So let's write down the conditions for these guys to be 0. So, or better, well, let me just sell. So A star gamma, the maximum value, is the minimum of xk, where xk minus 1 is the max between 0, A minus 1 v gamma k, A minus 1 dot t k. Okay, so this looks a bit fancy, but basically you are just solving this equation. You're just setting this equals 0. You solve it for A gamma, and you have to do that for each k. And then you figure out, well, I can only switch on the minimum possible amount, right? So you solve this equation, and you get several values, possible values for the A gamma, and you have to pick the smallest one, which is when the first vector reaches 0. Okay? So the other prescription for choosing the vector gamma is not based on the slope. It's you choose the vector for which the variation of the cost will be maximal. And that variation includes not only the slope, but that quantity. Okay, so you multiply the two. You try, for instance, you choose all local minima, including the global one, and you try for all these vectors. You play this game, and you see how much the cost will change, and you pick the one for which the cost will change the most. So that's the strategy. Indeed, the cost variation, delta C, is lambda dot v gamma plus C gamma times this A star. And this is negative. Okay? So again, once you do this, one of the vectors that was in the bases will disappear. So it has swapped with this new vector. And again, you have n vectors in the bases. So you go back to step 1 of the algorithm. Now you search again for a new vector. You bring it to the bases. You keep doing this until you cannot find any such vector. And at that point, the cost is minimized. Now, caveats. One caveat is it could be that this thing is infinite. Okay? It could be that no matter how much you crank up this new coefficient, the other ones will always remain positive. In that case, we'd say that the problem is unbounded. Okay? So the minimum of the cost is minus infinity. This can happen if you don't have enough constraints. What else do I want to say? Yeah, I think I've said everything I wanted to say about this algorithm. So again, you get a solution and you get a functional at the end of it. So you get both. So this, incidentally, this proves that the minimum of one problem is the maximum of the other problem. Okay? So questions about this? This is called the Simplex Algorithm by Danzig. It was invented in the 1940s. Yes?
How did you choose the cost function?
It just has to be linear in the OPE coefficients. The C's, they can be whatever you want. You choose.
What, do they correspond to anything, or the random?
Well, I told you. So suppose that you want to maximize one OPE coefficient. Then you pick all costs to be 0 except 1.
But why do I want to do that?
Well, this is one way of selecting out a particular solution in the space of CFTs. So typically what this is done is there is a very natural OPE coefficient to consider, which is the OPE coefficient between two operators and the stress tensor. Because in a local CFT, there is always a stress tensor. Okay? The other operators, they may or may not be there, but the stress tensor should be there. So it's natural to maximize the coupling to the stress tensor because it's a universal thing to do. Okay? And what that corresponds to is to minimize the central charge. So maybe Chris mentioned what this is, the central charge. It's a measure of the degrees of freedom in the CFT, in some sense. So when you maximize the OP coefficient, it's the same as minimizing the central charge. So it's like you're looking for the simplest CFTs, in some sense. So it's a natural thing to do. And besides, if you want to solve the feasibility problem, it's the same thing. So in this case, the costs are the costs of the auxiliary vectors. And you want to find out if the minimum is at 0. Okay? More questions?
Has it ever been the case that for two different cost functions you end up finding two different
Yes.
minimums?
Yes. Well, I can tell you a related thing is that sometimes the gap maximization problem, which I spoke about last time, so maximize the gap to an operator, can coincide with the minimization of the central charge. Okay? So for the 3D easing model, this seems to be true. We don't really understand why, but that's what happens. Okay? So. Okay, let me just show you some bits of this using Julia Boot. So this is a package for doing Bootstrap using Julia. So okay, we're going to look at the bootstrapping 4-point function of identical scalars. Okay, so this is this is to illustrate the simplex algorithm. So we set up one of these problems. I guess this is not working. Is it that it's just switching on? Or? Is it just because it's switching on? Or? Okay. Sorry about that, guys. So more questions in the meantime? So there's a completely different algorithm for finding the functional subject to the semi-definite constraints. Okay? You can solve it using the so-called interior point methods, which also can solve these problems very efficiently. Good. Okay, so you set up a linear problem. And so this is like step 1 of the simplex algorithm. So at step 1, so this is a case where you have 4 component vectors, n is equal to 4. And I'm working in 1 dimension. And so step 1 is we have a solution to crossing that only involves these fake vectors called auxiliary. So that's what that means. aux1, aux2, aux3, aux4. There are 4 auxiliary vectors. They have some associated OP coefficients. And the OP coefficients, they have to be equal to the target, right, by construction. And this is the negative of the identity. I shouldn't have run this, sorry. Okay. So let's have a look at the functional at this point. So that quantity that I wrote down. So when you plot the functional, recall that in order to find, you need to look at the functional and see where it has, when it acts on a vector, it's negative. Okay? And so you can see when you look at the functional acting on the vectors that it has negative regions. And so we're going to pick the vector for which the variation of the cost is maximal. Okay? So you ask the guy, okay, find me a vector which has for which the cost will decrease. This is called a vector with negative reduced cost. And it's found one. And if you include it, after 1 step of simplex, you see that now you have 3 auxiliary vectors and the new vector, okay, which is a vector of spin 0 and dimension 100, which is my cutoff. And the cost, now it's up there, but the cost has decreased. So, okay, so here it's 7, and before it was 177. Okay, so it decreased by a factor, it decreased by 100. Okay? So now you do this another 20 times, okay, it's changed again. The cost decreases. again, at this point, so for instance, at this point, after 20 iterations, you plot the functional and you see that it has a minimum at some point, so that's the vector that we're going to include. And so, okay, you keep doing this, and after many iterations, the minimum cost has been achieved. And if you look at the problem, in this case, the auxiliary vectors are gone. So the problem that I was solving was just, I was just asking, construct for me a feasible solution, okay, subject to unitarity. And so the cost, the final cost is 0, because the cost was proportional to the OP coefficients of these fake vectors. They're no longer there, so the cost is 0, and I have some solution to crossing. So if you take those vectors, the vectors with spin 0 and dimensions equal to those numbers, and you add them up, you get the identity, or minus the identity. Okay? So the simplex algorithm works. Okay, so now what can we do? Now we're going to construct a new problem where the set S is reduced. We're going to set a gap. So that's what that function there, filter, is telling you. It tells you, well, let's remove all operators of dimension below 2. And let's try to find a solution again. And look, now the optimal solution, so this is at the end of the simplex algorithm, the optimal solution has auxiliary vectors. So that it means that with this gap, there are no solutions to crossing. Okay? And if you plot the functional, you see that it's everywhere positive. Okay, so this is a log plot of the functional. So these minus signs are just the scale, because it's a log, right? It's positive, it has a 0 there. What's this 0? This 0, it's at 2. Well, 2 is one of the operators in the solution, right? One of the operators is at 2, and the other one is at 100. So if you looked at the function at 100, it would have a 0 there as well. So this is what I was telling you yesterday. At externality, the functional has zeros. The zeros are the vectors which appear in the solution to crossing. Okay? Okay, so now without a gap, there is a solution. And with a gap of 2, there is no solution. So now we need to search what's the crossing point. So we do this thing called bisection. And at the end of bisection, again, you plot the functional. It's positive. It has 2 zeros, one at 1 point something, another one at 4, and then it's just positive everywhere, which is what I told you yesterday. Externality, you have a solution to crossing, and you have a function which is positive everywhere, whose zeros are the vectors in the solution. So here is just a loop to do this many times. And then you plot it at bingo. So this is a bound. I don't know why this screen shows up so small, but so this is a bound on the operator dimension of the leading operator in one-dimensional CFTs. It's pretty boring. It's a straight line. But you can run this code in like 2 minutes. So for every value of the external dimension, the blocks change. So these V's, they change. So the final results will be different. And this is a bound. So everything that's below it, it's allowed. Everything that's above it, it's ruled out. OK? So this is how you do Bootstrap. You find an algorithm for constructing these functions, and then you play this kind of game. Okay? So questions about this? So now I just wanted to give you a small sample, some of the things that have been done with these techniques. So obviously, I showed you something in one dimension, but the Bootstrap doesn't care about space-time dimension. So let's do a bound in d equals 4. The original Bootstrap bound was done in d equals 4. The plot was not this. It was a bit, less, the bound was less constraining. So this is a plot in this paper that I'm citing there. The original plot was done by Hatazi, Richkov, Tony, and Vicky. And so if you need to read one paper on the Bootstrap, it's that one, which is the original one. Okay? So this is a universal bound on 4-dimensional conformal field theories. A bound on the dimension of the leading scalar operator in the OP. I mean, you have to think about it. The only ingredients that came into making this plot is conformal symmetry, crossing symmetry, and unitarity. That's it. So it's amazing that this actually works and gives you a bound. Notice that the bound, as the dimension goes to 1, it's saturated at 2. So do you know of a CFT which has a field of dimension 1 and fuses onto an operator of dimension 2? The free scalar. So the bound is saturated by the free theory. Okay. This is another very important result. I think it was the second paper. Now let's play the same game in d equals 2. And now the bound looks a lot more interesting. If you do problem set 2, you will get this plot. So you should do it. Not as good probably, but okay, you get the idea. So it has a funny shape. There seem to be two regimes, one above that red cross and one below. So this is what is called a kink. Bounds in the Bootstrap, sometimes they have kinks, and people keep hunting for these kinks. It's one of the names of the game in the Bootstrap. Why? Because kinks tend to coincide with interesting theories. In 2 dimensions, look, the kink, if you compare the dimensions corresponding to that point, they are 1/8 and 1, which are the dimensions in the correlator of the sigma field in the 2D Ising model. Okay? There are 2 operators of dimension 1/8 which fuse onto an operator of dimension 1. Okay? And the black crosses are other minimal models. So again, they seem to saturate the bound. And now one of the things that generated a lot of interest in this field is that if you do it in d equals 3, so d equals 4, the bound was boring. D equals 2, it was a bound that we already knew. In d equals 3, you get something that you didn't know, which is that the 3D Ising model, it's that little box, seems also to lie on a kink. The 3D Ising model is a lot harder, right? So there's no exact solution. There's not that much that's known about it, other than perturbative computations. Okay? And in fact, you can play this game. So I showed you 1, 2, 3, 4, but you can also do bounds in fractional dimension. And why would you do such a thing? You can, because if you want to compare with the epsilon expansion, it's useful, just as a sanity check. And so what you see is that there's a family of kinks in any dimension all the way down to 2. At 4, there was no kink, but then a kink appears just below 4, and then it goes down to 2. And you can compare the dimensions that you get from the Bootstrap with what's known from the epsilon expansion. So the orange bars are what comes from the epsilon expansion, and the black dots are the Bootstrap results, and so they line up perfectly. Now you can add many other bells and whistles. So something that you can do is add global symmetry. So now you consider the case where the scalars that you're bootstrapping, they transform as fundamentals of ON. What's going to happen is that those crossing equations will become vectors. There will be no matrices in this case, but they become vectors. And you can get bounds, and again, you can get it for any n that you want. You can even put fractional n. It doesn't matter for the Bootstrap, it's just a number. Okay? So in 2 dimensions, O1 you get Ising, then there's the O2 model, and there seems to be a family of kinks for any n. Okay? And it matches very well with what was known from Monte Carlo and large n expansion. Now, this is also very interesting, is what happens if you add information from multiple correlators. Now you're bootstrapping the 4-point function of the sigma field, and then the epsilon field, which is the scalar which appears in the OP of sigma with itself. And so subject to some assumptions, I showed you this bound in 3D, which had a kink. And when you add the information about other correlators, you see that the 3D Ising now lives on a little island there. Okay? So this is the first such result that was found. And by now, it's a lot more improved, as you'll see later on. Well, here it is. So this is a better result when you focus on that island. And so the box is the Monte Carlo results, the best Monte Carlo results, and this is what you get from the Bootstrap. And this was in 2014, so by now it's better. Again, you can do 2 ON, so now you get an archipelago instead of one island. The logic is the same. Now, I told you that when you saturate the bounds, you can read off the spectrum. So as a sanity check, you can consider the bound in 2 dimensions. Look at the functional near the kink. It will have zeros. Those zeros are operators which appear in the OPE. And so you just read them off and determine the OPE coefficients. Right? So the simplex method automatically gives you this. And so what this plot tries to capture, so I think, so the blue bars represent the exact results. So on the y-axis, the size of the bar is the size of the OPE coefficient. And we're showing for many operators with various spins and various conformal dimensions. So the blue bars are the exact results, and the red bars are what you get from the bootstrap. And you see that typically the leading operators, you can get them very accurately. So it's not really clear here, but you can get things with, I don't know, 6, 7 digits.
And you can get that for everyone on the boundary of that.
Yes. Here we chose the kink, but you could go on any other points. But then you need to be well motivated to understand, I mean, why those points, we don't know if they correspond to anything physical. So for the 3D easing, so this is what I was telling you before. If you, instead of doing this gap maximization problem, you do the minimization of the central charge, which is maximizing the OPE coefficient of the stress tensor, then you also see a kink. And the minimum of the kink is the 3D easing model again. So answering your question, if you can look at the spectrum at any point on the boundary, and so you can look at what happens across the kink. Why is there a kink? And you see that as you cross the kink, there's some funny transitions. There's on the left you see 5 operators, and on the right you only see 3. Okay? This is in the scalar sector, spin 0 sector. And in spin 2, the reverse happens. There are more operators on the right than there are on the left. So as you reach the kink, there's some swapping that occurs. And this non-analyticity is what causes the kink. Okay? We don't know why this happens. So this is just an observation. What we do know is that if in 2 dimensions the same thing occurs, and there we understand it as the decoupling of null states. Right? So in 2D, it's minimal models. Minimal models that are characterized, well, okay, maybe you don't know what minimal models are, but if you learn about 2D CFTs, they have a lot more structure because the conformal algebra becomes infinite dimensional. And anyway, this is what allows you to fix the properties of these models. And you can kind of understand why the kink is there in that case. But in 3D, it seems like a similar structure is there, but you have no clue why that's the case. Okay, so that's it. So I just want to finish with a little video. So I'm going to show you the best results for the 3D easing model in a movie, but I don't think you're going to get the sound, unfortunately. So this was submitted by David Simmons-Duffin, Alessandro Vicky, I think Philip Koz as well, and David Poland. So these are the current best bounds for the 3D easing model. And look at the scale. Okay? These are rigorous bounds, assuming that there's only. No, we do not want to watch this lecture now. So there are minimal assumptions like the existence of only one relevant scalar in each Z2 sector. So it's a universal bound on such CFTs. And well, there you go. So that's it. That's the end of the lectures. Questions?
Is it clear that if we do this good enough, that thing will become a point? Or
And there's no proof. But it looks like it. But yes, there's no proof. More questions?
Is there any notion of a null state higher CFT? Like,
I mean, you can certainly discuss null descendants, right? This is what I use to determine that recursion relation for the conformal blocks. But in 2D, this is something stronger. It's that certain primaries become null. These are primaries which are Virasoro descendants of other primaries. So you really need this extra structure to talk about them. In higher dimensions, that structure doesn't exist. So we don't know how to do it. One consequence of that structure is that in 2 dimensions, the conformal dimensions, they have like integer spacings between them. Okay? This is a consequence that there's some symmetry algebra with operators, with charges which have integer dimension. In higher dimensions, you don't expect this to be true, and indeed, the conformal dimensions that you get, there are some crazy numbers. So it's very hard to understand what this could be. Yes?
Can you bootstrap a model in 2 dimensions with central charge 0, like string theory?
With central charge 0. I'm not sure what you mean by that. So that's, strictly speaking, has no local operators, right? If you couple to gravity, then you lose local operators because they are not gauge invariant. So C equals C very small would mean that the OP coefficient of T is very, very large. So if you want to do that, you just, you go through this game and you just put in by hand. So you have the identity on the right-hand side, and you take the stress tensor and put it here on the right-hand side with a fixed, very large coefficient. And then you would play the same game. This is how you could do what you're describing. And no one has done it, as far as I know. People usually do the reverse. They try to no, sorry. Is this, no, we are doing this. We are minimizing the central charge. So you can prove in some cases that it cannot be below some results. So that curve that I showed you tells you that the central charge cannot be below that value, so it cannot go to 0. This is in 3 dimensions. Although in 2D, there's also similar results. So yeah, sorry, this has been done. Yes?
In the radio, do you know what's the condition that you get a small island?
Sorry, in the what?
In the radio, you get a small island application model. Do you know what's the condition that applies to get a small island?
The condition to get smaller island. The condition is to have good computers.
Just high derivatives.
That's the condition.
That's the only condition.
No, there are a few more tricks, but I don't want to get into them. These are reasonable things, reasonable assumptions that you should do, like demanding that there's only a single relevant scalar, and then you only expect that, yes, well, it's this, that there's a single Z2 even scalar, for instance, single Z2 odd scalar, which is relevant. So if you demand these 2 things, you have to work a bit, but this is the result that you get. And then, yes, if you want the island to shrink, you need more computer power. The story of this video is the story of using these tricks and more computer power. More questions? Yes?
One question. As the island shrinks, are we still on the king, or?
So this is the kink. And so you're putting some extra constraints which cut off some small region, or maybe like this. Well, the kink is a bit fuzzy, so it's not as sharp as I said here. Right? It's more like a transition region. And so basically you're cutting a region that looks like this.